Hello everyone, this is Sakshi and I welcome you all to my edutech platform, Way to Learn. So before we go into the video, like my videos, share and subscribe my channel and do not forget to hit the bell. So let us go into our video which is quantum mechanics and it's part 7. So in this video we will be learning some important points on the wave function. We'll learn more important points like information of wave function, what is a wave function, where is it used, how is it used in my upcoming videos. So we know that de Broglie wavelength is lambda is equal to h by p. So h is the Planck's constant and p is the momentum over here. So a particle has both particle nature and wave nature according to de Broglie hypothesis. So I can say that a particle can behave as a particle nature, it has a particle nature, or it has a wave nature, not both at the same time. It only has one of these two natures, but not the both at the same time. It can either behave as particle or as a wave. Okay, so if my particle behaves as a wave, I can say that this matter which behaves as a wave should be represented by a wave function. So I am representing these matter waves in the form of a wave function, say psi of x. So now if my particle is present, so this is an important point. Now if the particle is present, then it should have a wave nature. So that wave nature is represented by a wave function. So if a particle is present, then there is psi of x. So there is a wave function. So wave function will not go to 0 when a particle is present. So if there is no particle, then no wave function, then you can directly put our wave function equal to 0. So you have to remember this. It can be asked in any multiple choice question. So now if the particle is present, so we have two cases if the particle is present. It can be in rest or it can be in motion. So now, how can you write this wave function? Obviously, if there is a particle, you know that wave function is present, then our wave function psi of x should not be equal to 0. So now, if the particle is at rest or if the particle is at motion, then psi of x will not be equal to 0 in both the cases, but our wave function will be constant if our particle is at rest, and our wave function will be a variable if the particle is in motion. So remember this, if your wave function is variable, then the particle is in motion, and if it is in rest, then our wave function will be a constant. So now this wave function defines the state of the particle. If it is if it is a constant, that it can say that the particle is at rest. If it is a motion, we can say that wave function is variable. So using this wave function, we can get lots and lots of information of this particle because this particle is acting as a wave. It moves as a wave. So this wave function which defines that matter wave will have a lots of information about this particle. So basically we need the information about the particle, in which energy it is in, what is the momentum, what is the position. So we need all these kind of information. How do we find that? So we need a wave function and we have a wave function. Now having this wave function, it can either be a constant or a variable. How can we find the energy, momentum, Hamiltonian of this particle? So since psi of x has a lot of information, we need to get all this information from the psi of x. We require an operator. So an operator is required to act on this wave function. So this operator will basically act on that wave function and give what we need. So if we want to gain an energy, we need to find the energy of that particle, we will use an energy operator and it will act on the wave function and it will give the information of the particle in which energy is it in. Similarly, if we need the momentum, we will use the momentum operator. So we'll go and learn about the operators in further videos. So but we need an operator in order to get information about the particle. So I can say that this is some normal operator. Let me say that operator is A. It acts on a wave function psi of x and it gives some value. So that will be the information about the particle. So that value is given as A over here and again the wave function. So if you see this equation, you can easily find what equation is this. This equation satisfies the eigenvalue equation. You can say that this is an operator which acts on an eigenfunction, gives us an eigenvalue, and that eigenvalue will be the result of the particle. Whatever operator is operated on it, that will be the answer. That eigenvalue will give us the answer. So if I operate with an energy operator, my eigenvalue of that equation will be the value for that particle. It will give the energy of the particle. So eigenvalue gives me the answer or information about the particle whenever an operator operates on a wave function. So here A is considered as an operator, wave function is an eigenfunction, and A, which is the answer or the result of the particle, is the eigenvalue. So the operator satisfies the eigenvalue equation. Therefore, I can say that we actually know basically in quantum mechanics, these operators are Hermitian operators. Only Hermitian operators can act on a wave function. You can remember it in a way that all the operators that operate on a wave function must be Hermitian operators. So, have you learned Hermitian operator? If not, just go into my mathematics video and you'll learn that over there in matrix video. So here you can, like, in Hermitian operator, the eigenvalue that is obtained are all real. So if you need to get an information about particle, you will obviously need a real value, not an imaginary. So I can indirectly say that to get a real value, my operator must be Hermitian because it obeys the eigenvalue equation. Therefore, if my operator is Hermitian, it will obviously give me an eigenvalue which is real. And that eigenvalue will be the result. So, I can say that the operators used in quantum mechanics are Hermitian operators and those eigenvalue obtained must be real always. So now, that's all about the operator stuff. Let us go something about the wave function. Let us consider a particle in a system. I can say a particle is in some system here. It can, now this is a box, okay, and it has energy levels like E1, E2, E3 and so on. Now I do not know where my particle is. It can either be on E1, it can be on E2 or E3, but I do not know. So if it is on E1, it can have a wave function psi1. If it is on E2, it can have wave function psi2 or psi3 if it is in energy level E3. Now, the problem is, I do not know in which, like, we do not know in which energy level my particle is present, right? So, for one particular particle, there are these many wave functions, right? If it is in E3, then it will have psi3, and if it is in E2, it will have psi2. So, I do not know which wave function to be used in order to obtain the information about the particle. So, over here, I am going to assume a bigger wave function which defines all these smaller wave functions psi1, psi2 and psi3. So that is called a superposition of wave function. So phi will be my wave function which defines which defines the system, the wave function of the system in which my particle is present. I do not know now that if it is in E1, E2, O3 or E3 or in any other energy level. So I can say that phi is my main wave function in which has like psi1, psi2 and psi3 or sub wave functions. So phi is the main function which contains all the sub wave function. Now it would be easier if I collapse my wave function. Now on like measurement, this is an important information, just write down that I haven't written over here. Now if you have a wave function which is equal, there is superposition of wave function, you have a superposition of wave function, and now after doing some measurements, I say that my particle is in energy level E2. So I am exactly saying that my particle is in E2. Then I do not want these other wave functions psi1, psi3, psi5, psi4, anything else. I do not need anything else. Okay, I just need psi2 because after measurement I know that my particle is in E2. Therefore, I would require my wave function to be psi2. That is, the main wave function should be equal to psi2, because now after measurement, my particle is in E2. I will have to use only the wave function psi2. I do not need any other wave function over here. It might cause a problem while solving a problem. So, now what do we do in order to get this phi equal to psi2? We can collapse this wave function. So how do we collapse this wave function? This is basically nothing. You just have to remove everything and just give this main function phi will be equal to psi2 only after knowing in which level is your particle. So if I say that my particle is in psi3, so after collapsing the wave function, my main wave function phi will be equal to psi3. So that kind of work is called as collapsing of wave function. Okay, the main wave function is collapsed right now. So I can say that my wave function is collapsed, and therefore I can, after measurement, my wave function gets collapsed. But before measurement, my wave function will be a superposition of wave functions. Okay, it might be confusing, but please just uh, write those notes and also read in a book, like read in any quantum mechanics book. It will be helpful. So next, this is a small basic information about wave function, where it can be represented in two forms: as a function like psi of x, or as a vector form. It can be written as bra vector or ket vector. So basically, ket vector can also be written in column matrix, and bra vectors are usually written in row matrix. So about the bra and ket vectors, whenever we use that, I'll be giving information on that. So I'm not going to post other video for bra and ket vectors, but they have many properties. But while we use those in our problems, or while we do any other while I provide any other information, I'll also provide information about these vectors. So basically, if bra vector is over here, like I can say that my ket vector doesn't do anything. Okay, it doesn't affect anything. But if it is in the bra vector form, then you have to change it into a ket vector. If you have to change my bra vector into a ket vector, you will have to take the transpose conjugate of that. So bra vector affects the wave function, whereas ket vector does not affect the wave function. So for example, I write my ket vector to be a e power ikx. But if I write that in my bra vector form, then it is obviously changing the wave function into a e power minus ikx, because I am taking the transpose conjugate. So this is a important thing. So ket vector does not affect my wave function, whereas the bra vector affects my wave function, because we have to take the transpose conjugate of that particular wave function. So this is that much about small information about the bra and ket vector, how we can write the about the wave function, and few important points on wave function operators. So I hope you like this video. So thank you, and support me, and also share my videos and subscribe my channel. So see you in my next video with more information on the wave functions and operators. So thank you. Ta-da!